welcome to the next session of Strength of Materials. In this session, we are going to discuss about statically indeterminate shafts. A shaft which is constrained to have free rotation by having fixed support at its ends are said to be statically indeterminate shaft. You can see over here, this is a shaft AB. Both its ends A and B are fixed. Analysis of such a shaft is done by combining equilibrium equations with equation related to angular displacement. So we are going to use an equilibrium equation, that is summation of torque over the entire body is 0, and we are also going to talk about angular displacement, that is theta. Now if you look at this shaft, A and B are fixed, so I have drawn the FBD over here. In the FBD at end A, I am showing a torque with an assumed direction, and at B again I am showing a torque instead of this fixed support, and the direction for both of them are assumed. Now let me say that this torque at C is in clockwise direction, so I am taking the torque at end A in counterclockwise direction and at B also in counterclockwise direction. This direction of TA and TB is purely an assumption. If I solve the numerical and I get positive answers for TA and TB at the end, I would say that the direction that I have assumed is correct. If not, then I will change the direction of the torque. If you understand very clearly, this value of torque T at end C is something that is given to me in the question. TA and TB are the resisting torques because they are fixed ends, so they are going to resist the twisting of the shaft by the application of torque T. So we will be calculating TA and TB in the numerical. Now here what we are going through is just the applicable equations. The first equation that is applicable is summation of torque over the entire body is 0. So I can say that TA plus TB will be equal to the torque T. This is one of the equation. Now the next equation is for this angular displacement, as it is mentioned here, that is twist in the entire body is what I am going to calculate, and the summation of twist over the entire body is also equal to 0. So let me talk about the twist in the portion A to C plus twist in the portion C to B. It is A to C, C to B is equal to 0. Now suppose if I say that theta AC is equal to minus theta CB. If I want to change this direction of theta, what I'll do is I'll simply write theta C to A is equal to theta C to B. So I've just changed this direction of analysis. So that's how we can also write this equation, or if you want you can just leave it this way itself. Now let me substitute over here. We know that T by J is equal to G theta by L. So theta is nothing but TL upon GJ. So let me substitute here. Let me talk about shaft A to C. When I am standing at A to C portion, you can see here, I can either say that the torque is TA because that is the torque on one side, and when I stand at the junction C, I can see a torque T which is going clockwise, and I can see another torque TB which, by using principle of superposition, I am going to assume its effect at the position C. So I will be getting a subtraction between these two values. So I can simply write by seeing the junction A. So you can either focus on junction A or on junction C. I would prefer junction A because there is only one torque at junction A, and that is obviously going to be the answer. So here I am going to write down TA. The length for the first shaft here is L1 upon G1 J1 plus for the second portion of the shaft, that is C to B, I will focus on junction B because at junction B the torque TB is very clearly visible. So I'll write here it is TB L2 G2 J2 is equal to 0. Now if you observe, this is just one particular shaft. So the diameter is going to be equal for both of them. So I can say J1 is equal to J2. Hence I'll have TA L1 upon G1 plus TB L2 upon G2 is equal to 0. So this is another equation that I have. I have one equation over here and equation over here. So these two equations can be used for calculating value of TA and TB. Now in this case of TB, I just want to mention here, instead of TB, suppose when I am standing at junction C and I look over here, I can see that TA is the torque whose effect will be considered at junction C, and T is another torque. Now for finding that value, I can directly use this equation which I have over here. Instead of TB, I can write very easily that it is T minus TA. So I can write here T minus TA as an equation if I want to, and T is a value which I know, so the equation will now be in terms of TA only. Similarly, instead of TA, if you look here from this equation, I can write it as T minus TB. So it can also be written as T minus TB into L1 upon G1 plus TB L2 upon G2 is equal to 0. Now this entire equation becomes completely in terms of TB, so I can find the value of TB. So these are the equations. Now we should know the equation for maximum shear stress. So for shaft 1, I am calculating tau max 1. It is 16 T upon pi d cube. Now diameter is say d1, and torque for the first shaft or between A to C is TA. For shaft 2, tau max 2 can be calculated as 16 TB upon pi d2 cube. So this is the way for solving for an indeterminate shaft. Now let's talk about another case over here. This is my second case, a shaft wherein we have 3 attached shafts in series and they are between 2 fixed ends. So this is the FBD which I have drawn. At end A, I have assumed a torque TA which is of resisting nature, and at end D, again there is a resisting torque TD. Now TB and TC values will be given in the question. So let me assume that TB is clockwise and TC is clockwise. That is given to me, and TA, let me assume this as counterclockwise, and TD again as counterclockwise. So we will write the applicable equations again. The first one will be summation of torque over the entire body is 0. Since TA and TD are in the same direction as that of TB and TC, this will be my equation. Second one will be summation of theta over the entire body, that is from A to D, will be equal to 0. So this will be theta A to B plus theta B to C plus theta C to D is equal to 0. That is the angular displacement for individual shafts. So when I am standing at end A for this portion AB, when I am calculating here, this will be directly TA L1 upon G1 J1. For the second portion, now when I calculate for the second one, I will suppose stand at junction B. Already at junction B there is a torque TB which is acting, and the other one is going to be my TA whose effect I am going to consider at point B. Now they both are in opposite direction. So let me assume that TA is greater than TB. So I take this as TA minus TB into L2 G2 J2. And for the third portion CD, let me stand at junction D so I can see the effect of TD over here. So this is TD L3 upon G3 J3 is equal to 0. You can write these torque again in any other fashion that you please to. Now let's write the third equation, that is for shaft 1. The formula for tau max 1 will be 16 TA upon pi d1 cube. For shaft 2, tau max 2 is going to be 16 Ta minus Tb upon pi d2 cube for shaft 3 tau max 3 is going to be Td into 16 upon pi d3 cube. Now here the maximum value of shear stress in the shaft will depend on the torque Tb, Tc that is applied, the value of those torques, and also the diameter of the shaft that is given. So here we directly cannot say that because the shaft 3 has minimum diameter, hence the tau max will be for shaft 3. That is not the case. It also depends on the value of Ta, Tb, Tc, Td, all these terms. So with this, I end the theory part of statically indeterminate shafts. In the next session, we are going to discuss numericals on this topic. I hope you have understood the lecture. If you have any doubts, please write to me in the comment section. See you in the next session. Thank you.